So now that we've covered the odds ratios aspect of things, let's kind of go back to that lethal distance, or kind of a lethal dose, more specifically, that we talked about earlier. So we're going to go back to where we were using just distance as our explanatory variable, not that change variable that we looked at previously. So I'm going to refer to this as a lethal kick, just since we're not talking about something pharmaceutical or dose. Might seem to actually make more sense. So suppose I would like to find what distance I would be kicking from to have a 25% chance of success, a 50% chance of success, or a 75% chance of success. So I'm going to refer to these as lethal kick 25, lethal kick 50, and lethal kick 75. So now we did talk in the very first video about how we would use this formula to help us calculate it. All right, so here's sort of our generic formula that we have. We've been given now values of pi x to be able to use. Now that I've fit my model, I have estimated values of alpha and beta. So since those will be estimated values, I'm going to be putting a hat on top of x as well, simply because we are now estimating that value versus knowing the true value. So let's go ahead and do them first here by hand. So when I'm wanting to do that lethal kick of 25, my x hat is going to be our natural log of 0.25, because we were interested in that 25%, over 1 minus 0.25, or 75%. And then we're going to subtract off alpha hat and divide by beta hat. So as a refresher of where we have those values, so again, we're going back to where distance was our explanatory variable. And here's that alpha hat that we have and our beta hat. So those are going to be the values that we're going to use in our formula here. So our alpha hat was 5.78182, and then our beta hat was negative 0.1145. Doing that math, we should get a distance of just a tad bit over 60 yards. Or again, what that would mean is if I would like to have a 25% chance of making the kick, I could do so from about 60 yards away. Now we can do the same thing for a 50% chance. So the only thing that's going to change in my formula are these two values, because I still have the same alpha hat and beta hat, because I'm still working with the same data set. So the only thing that's going to change are the two numbers that we're plugging in here. So now my estimated distance will now be the log of 0.5 over 1 minus 0.5, which is also 0.5, minus our alpha hat, divided by our beta hat. And that should give me a distance of about 50.5 yards. So to have a 50-50 chance of making that kick, I could do so from about 50 yards away. And then of course, similar idea here for the 75. Again, the only thing that's changing is what is inside the log piece of what we're doing here. Still subtracting off that alpha hat and still dividing by our beta hat. And this time I would get about 40.9 yards for my lethal kick distance. So if I want to have a 75% chance of making it, we can do so at about 41 yards for our kick. So those really weren't too bad to do by hand, but let's also show you how we can do this in R. So first, looking at the code here in our handout, the first thing I'm doing is creating what I'm calling my pi.vec, which means just a vector of my different values of pi that I'm interested in. So notice we were using the 25, 50, and 75, so I'm using the 0.25, 0.5, and 0.75 equivalents for each of those. So I'm just going to be able to do them all at once this way. And then I'm calling what I'm storing this as my LK for lethal kick. And then I'm really just plugging in the formula that you see here, but at each place where I had these different values, I'm actually going to be using my pi.vec, and that's going to allow me to do it now for all three at the same time. So we would take the log of whatever pi is, divided by 1 minus pi. Then we needed to subtract off that alpha hat, which is just that mod.fit $ coefficient, the first element, and my beta hat's just the second element. Then I'm just storing them a little bit more pretty, so that I actually have my values of pi with the lethal kick here together by putting it in a data frame and then just printing those out. So now actually doing that here in our so there's my pi.vec, calculating the actual lethal kicks, putting them in a little bit more of a nice data frame, and then finally printing them out. So now we see that 60.09 yards, 50.5 once we round that, and 40.90 there as well. So you could do that for any of the different values of pi, so you could plug in different values here if your interest was in different values for your estimated probabilities to be. There's also a nice function in R that will do this for us. The first thing I have to do though to actually get this to run is I need to run a new library into R. I want to get the mass library. Now when I run this in R, it's just going to be loading some functions and packages for me that I'm going to need later. So it's not going to actually spit out anything once I run that code. Now once I have that library installed, there's actually a function called dose.p. That's the name of the actual function, so I can't change that. I'm going to store what I'm doing with this function into what I'm calling save.lk. So it understands that idea of finding a lethal dose is a very common thing that people would like to do. So this function does it for us. The two different things that it needs to know is it needs to know the fit of your model. So this mod.fit is where I stored my original model up here, where I have predicting the success based upon the distance. And that's what I named storing that. So that's what I need here as well. And then it needs to know, well, what values of pi do you want to do it for? And so I've already put these in what's called pi.vect, and that's going to be what's called the p that it needs. So when I run this function, it's going to go ahead and already have those values done for me, and now I'm just spitting them out. So it gives me those values of pi there that I wanted. The dose would be our distance that we actually calculated those for. And it does also give us a standard error, which could be very useful if you wanted to do a confidence interval. So how would I actually do a confidence interval? Well, I could do one through a pretty easy basic walled way of doing that. So what we could do is we could take our x hat, or in that output is labeled as our dose, plus or minus a z times our standard error. So that's one of the benefits of doing it this second way versus doing it in a sense by hand, is we're able to get that standard error to allow us to create a confidence interval. Right, last thing I want to do here with the lethal kicks is actually show these on a plot. So the first thing I'm going to do is sort of create our basic plot in a very similar way. The main difference I'm doing here is I'm not going to create a bubble plot, I'm just going to create little dots. So I'm not going to use the different sizing function. All of this that you see here is stuff that we've seen before. So if you have questions on any of this code, I'm going to kind of run it piece by piece and re-explain what each piece is doing. But we did this in our previous module as well. Right, so again, first this library that I'm running is so I can get this G summary function is the reasoning why I'm actually running this library. The first one that we're doing is just creating a data frame with just the two variables that I need it. So I want my distance and whether or not that kick was good. So I'm just getting a data set with just those two variables in it. Now I'm going to summarize this new data set and get two different values from it. One I want is going to be the sum. That's going to again give me my number of successful kicks because it's going to be adding a whole bunch of zeros and ones together. And then I'm going to get my length, which will tell me how many kicks were done at those given distances. So we're going to get the number of successes and the number of attempts for each distance. So that's again what those two lines are doing. Now I'm going to create those sample proportions by looking at my number of successes divided by my number of attempts. Then I'm just putting this in a nice data frame here again, and I'm spitting out the first 5 rows so we can see what it looks like. So again, here's our number of successes, number of attempts, that sample proportion, so 2 out of 3 gives me that, and also tells me what distance that was at. Now because I'm going to want to put the fitted model on my graph as well, that's why we're doing the next part here. Sorry, after my plot. So there's my plot, there's my actual data put on my graph. Now we're going to put that fitted line of our logistic model with the logit link. So I'm going to put in all those different distances, create my alpha hat plus beta hat times x, and now actually get that pi hat, which is e to the alpha hat plus beta hat x over 1 plus the same thing there. And then putting that line on the actual graph. So all of that we've done before, technically nothing new. The next part is really the new part. I'm going to actually put the lethal kicks on the graph. So thinking about what I'd want to do with this. So I want to say, well, if you have a 75% chance, that's what you would like to have of making it, where does that distance fall? So since we're doing that backwards prediction, if I want that 75%, where am I going to fall down there? So I'm going to be putting some line segments on here. So the first one is actually going to give me my actual distances. Let me make this a little bit bigger so we can see hopefully more of the code there at the same time. So when you do the line segment, it needs to know the x coordinate and y coordinate it's going to start from. That's what x0 and y0 is to tell me where it's going to be. Here I'm using that lk.summary. If we don't remember what's in that, going up here. We can run that piece again if we're unsure. It has the pi-vec and the actual distance of the lk in it there for me. So I'm going to use that lethal kick. So that's going to have my 40 yards, my 50 yards, and my 60 yards. That's going to be my x starting point. My y starting point is going to be at negative 0.1. That way it's just going to kind of start about right here. And right here, and right here. So for each of them, it's going to do me 3 lines at the same time. Then for the ending point, you need an x1 and a y1. My x1, the x's are not actually going to change. It's just going to be a straight line that's going to go up. So that's why you see that x1 and x0 are exactly the same thing. What's going to change is where I'm going to draw the y up to. I'm going to draw the y up to my 75%, 50%, and 25%. Then I'm just putting some different line types and different colors on it for you. So if I'd run just this line of code, it's going to put these 3 dashed lines here. That one about 40 yards gives me that 75%. That 50.5 yards gives me the 50%. And that 60 yards will give me the 25%. So it's giving me lines to kind of show you how I created those numbers. The next line segment is really just doing the same thing of doing the 75% to match up over here, the 50% to match up over here, and the 25% to match up over here. So this time I'm going to be drawing horizontal lines. So my values of y are going to stay the same versus my x starting points are going to be different. Because of how my plot is scaled, I'm starting my x at about 15, because that seemed like a reasonable to make sure I can actually see the entire line. And it's going to end at whatever distance that it went to. My values of y are just going to be that 25%, 50%, and 75%. So when I draw those, you're going to now see if I need that 75%, a little bit more than 40, 50% a tad bit more than 50, and for 25% a little bit more than 60. And then the last 2 lines of codes here are just putting that legend where you can click where you want to put it, which we did something like in the previous module as well. So that's what our plot looks like. And it's just kind of nice so you can see where the different values actually fall. So there's our plot. The last question to answer in this video, would it make sense to do this for the explanatory variable change? Why or why not? So first, as a reminder about this change variable, change was a binary variable where it was equal to 1 if a lead change could happen and 0 if there was no lead change, even if the kick was successful. So because it only has 2 options, or if I just only have zeros and ones, it doesn't really make sense to look at. So I would not want to do this because it's a binary variable. So I really only want to do this lethal dose idea when it's a quantitative variable or a continuous variable that I'm really working with. Right, in the next video, we're going to be picking up with doing some confidence intervals for many of the things that we've talked about thus far.